Page 2 of our sample test. We're going to have here to start with, make sure you can see that. Yeah. So it says solve these. Well, 9 to the 2x plus 1 equals 27 to the 2x. 9 and 27 both are powers of 3, which makes this easy to solve exactly. This becomes 3 to the second to the 2x plus 1 equals 3 to the third to the 2x. And so when I got a power to a power, I can multiply the powers, and they have the same base, so the powers have to be equal. So I'm going to get 4x plus 2 has to equal 6x. If I subtract 4x from both sides, I get 2 equals 2x, divide by 2, and I get x equals 1. Then I should check that. So I put 1 in here, I get 2 times 1 is 2, plus 1 is 3. Is 9 to the third the same as 27 to the 2 times 1 is 2, 27 to the 2. And you can type that into your calculator and you will see that those come out to be the same. Okay? Next one. So the x is not over here, it's in the log, and so that says to me right away, if x is anywhere on the log side, to rewrite this as a power equation. And it says, to what power do we take this to get x? We take this cube root of 5, to the 6th power to get x. Now, cube root is the 1/3 power, so we have 5 to the 1/3 to the 6th equals x. What do? We multiply the powers. 1/3 times 6 is 2. So we have 5 squared is x, and so that turns out to be 5 squared is 25, and that's what x is. Now, C, when you have logs on both sides, you like to get it down to a single log on each side, and then you can set the arguments equal. So we have the log in base 10 of 5x plus 2, and on the other side we have 2 log x, and so the 2, according to the power rule, can go up, and so this could be the log of x squared, plus, and now this is log of 3, and when it's plus, the plus rule says you can change the log of something plus a log something becomes the log of the product of those things multiplied. So times 3. So now this has to equal this. So we have 3x squared has to equal 5x plus 2. You should recognize this as a quadratic, and when you have a quadratic you should set it equal to 0. So you're going to have 3x squared, subtract 5x from both sides, makes 5 minus 5x. Subtract 2 from both sides, you get minus 2 equals 0. If we factor that, we get 3x and x. And to make minus 2, we're going to have a 2 and a 1, and one of them is negative. We've got to get minus 5. So if I put one of them is negative and one's positive, so I better get 6 minus 1 to get 5. So I'm going to put the 2 here and 1 here, so I get 6 x's and 1 x, and I want it to be negative 5, so I'm going to make it negative 6x plus 1x is negative 5x. So setting this equal to 0, I subtract 1 and divide by 3, and I get x equals negative 1/3. Setting this equal to 0, I get x equal to 2. Now, can I use either or both of these? And so I go back to the original equation. If I put negative 1/3 in here, 5 times negative 1/3 is 5/3 plus 2. That's a positive value, but I can't put negative 1/3 into this one because I can't have the log of a negative. So negative 1/3 has to be thrown out. Can I put 2 in? So this would be log of 10 plus 2, 12. And this would be the log of 2 log 2, which I can do, and a log of 3. And so that tends to show that works. Now you can actually work those out by typing them into calculator, and you'll see that you get the same decimal for both sides. Okay, D. We have 5 times 3 to the x plus 1 equals 7 to the negative x. All right, so we have a problem here that things are not the same base, and there's no way to really make 3 and 7 be the same base because there's not a common factor in them, like up here where 9 and 27 were both powers of 3. So we're going to have to change these to the same base down here. So let's just say I go to base 10. So 5 is 10 to the log 5 times 3 is 10 to the log 3, and that's to the x plus 1. 7 is 10 to the log 7, and that's to the minus x. So now, this says I need to multiply these two powers when I got something to a power. And when I multiply two things with the same base, I add the power, so I get log 5 plus log 3 times x, so I'm going to write that as x log 3. Log 3 times 1 is plus log 3 equals negative x log 7, multiplying those. Now I have x in this and x in this, so I'm going to subtract this one to the other side. So I'm going to have log of 5 plus log of 3 equals negative log x log 3, subtracting that one over, minus x log 7. There's an x in both of these, so I can factor it out. That's the tricky part. And I get negative log 3 minus log 7 equals log 5 plus log 3. And then I can divide both sides by this, minus log 3 minus log 7 minus log 3 minus log 7, and x is this value. Now, if I have addition of two logs, that can turn into a product, so that turns into log of 3 times 5, or 15. And the negative on this could be pulled out, and then I would have log 3 plus log 7, so this could be negative of log 3 times 7, 21. And a negative on this would, well, we'll just leave it like that. That's good enough. All right, E. So now I got log of two things here, so I'm going to combine those, and it's subtract, so I'm going to have log, the subtraction rule says goes to a quotient, that's x plus 21 over x equals 2. Since there wasn't a base, that means it's a base 10. So since there's an x with the log, I'm going to change it to a power. So I'm going to have 10 to the 2 equals this. 10 to the 2 is 100. Equals x plus 21 over x. I'm going to multiply both sides by x. So I got 100x equals x plus 21. I'm going to subtract x from both sides, and I get 99x equals 21. Divide by 99, and I get x equals 21 over 99. See, 3 goes into both of those. That's 7 over 33. That's what x is. Okay, number 4. A. So we have radioactive isotope that's decaying according to this rule, where A0 is the initial amount and T is the number of days. And it says determine K if 10 grams decays to 2 grams in 30 days. Well, A0 is the starting amount. The amount after some amount of time is A sub T. So it went from 10, so the starting amount, so in this formula that says A of T equals A at the beginning, E to the KT, and in the beginning it was 10, so I replace A sub 0, the beginning amount, with 10, E to the KT equals A of T, and then after 30 days, and T was days, so if I put 30 in for the T, so I'll have 10 E to the 30K, the amount that was left is 2 grams. Now to solve for K, let's get rid of the multiplied thing first. So we'll divide by 10, and so we get 1/5 equals E to the 30K. The unknown is a power, so I write this as a log. This says, to what power do I take E, so that's ln, to what power do I take E to get 1/5? And the answer is 30K. So I'll take and divide by 30 on both sides, and I get K to be ln of 1/5 over 30. So now I know my full equation is the amount that'll be left at some time will be the starting amount, which is 10 grams, E to the K, which is this number. Let's get the decimal approximation of that. So I'll pull out the calculator and I'll go ln of 1 divided by 5, and that answer divided by 30, and I get negative 0.0536. So I get negative 0.0536 T. So now if I put in the number of days here, this will tell me how much will be left after that many days. How much of the 10 grams is still radioactive after 10 days? So I put 10 into this. So I'm going to get 10 E to the negative 0.0536 times 10. And it says 5.85 will be left. For B, 5.85 grams. C, in how many days will 30% be still radioactive? Well, 10 times, this would have to be 30%. 30% of the 10 would be how much is left. So I got to make e to the negative 0.0536 t equal 30%, which is 0.3. This is where I got to find the power. So I'm going to rewrite this as a log. So to what power do I take e to get 0.3? And that is the power is negative 0.0536 t. So I will take and divide both sides by that negative 0.0536, negative 0.0536, and so I got ln 0.3 divided by negative 0.0536, and I get 22.46 days. Okay, what's the half-life of this asymptote? So when is it 0.5? Half as much, 50% there. And so I'd solve this using 0.5 over there, and so it's going to be ln 0.5 divided by negative 0.0536, and the half-life is, I put a negative, I forgot to close the parenthesis on the ln. Second enter, go back here and insert the parenthesis, and I get 12.9, 13 days. All right, that's it.